Hello everyone, my name is Tatsuma Mori. I will now start my presentation of fast and memory efficient approximated convexal computation with FPGA from now on. The table of contents is as follows. First, I will explain about the convex hull. A convex hull of point set is the set minimum convex set surrounding point set. In 2 dimensions, convex hull is a polygon as shown in the figure. Convex hulls can be applied to wide range application fields. Applications include, for example, Voronoi diagram construction, diameter computation, and design automation. In addition, convex hulls are also used in processing that require real-time performance, such as collision detection and path planning. Moreover, real-time algorithms were proposed. Therefore, FPGA implementation should be suitable for these real-time processes. Next, I will introduce 4 related works that implement convexal computation on GPU. In the first work, the convex hull was computed using GPU and CPU. Performance evaluation with GT640 and GTX 660M GPUs showed that this method achieved 6 times speed up compared to library Q-hull. In the second work, they implemented the quick hull algorithm on GTX 280 GPU and achieved up to 40 times faster performance than Q-hull. In the third work, they implemented the quick hull on GT280 GPU and achieved 10 to 50 times faster performance than quick hull implementation on CPU. In the fourth work, they proposed a general-purpose framework for divide and conquer method on GPU and applied it to quick hull. They achieved a speed up of 10 times or more compared to the quick hull implementation. These methods cannot start the computation process until all the input points are given and are stored in memory. Thus, they are not suitable for real-time processing. On the other hand, there is work that implements convex hull computation on FPGA. That is this work. In this work, they implemented the monotone chain algorithm on FPGA. This algorithm needs to sort a given point set as a pre-processing step. However, this approach eliminated the need for the processing sort by detecting the point set coordinates while scanning the input image with a raster scan. In this work, point detection and convex hull computation are executed in parallel. Thus, it is more suitable for real-time processing than the previous GPU implementations. However, it cannot be applied to general systems where the input points are not pre-sorted. Therefore, the purpose of this work is to implement FPGA so that it can be applied to the general system where needed to handle unsorted input points. To find the convex hull of unsorted points, it is necessary to store all points into the memory before starting computation. However, it is not realistic to store a large number of points in a FPGA with a small on-chip memory capacity. On the other hand, depending on applications, computation speed is more important than exact solutions. In such cases, an approximation algorithm may be used. In fact, several approximation algorithms have been proposed. In this work, we propose a method to compute the approximated convex hull while storing only parts of points in the FPGA and implemented and evaluated. Then it is a summary of the purpose of this work. To find the convex hull of unsorted points, it is necessary to store the all points into a memory before starting computation. However, it is not realistic to store all points on FPGA in terms of memory capacity and latency. Moreover, FPGA implementation in related works require pre-sorting of input points. Furthermore, the approximated convex hull may be used instead of the exact convex hull. Therefore, in this work, we propose a method that finds an approximated convex hull while storing only parts of the given point set in FPGA and evaluated the execution time and the approximation accuracy. Next, I will explain the computational method of convex hull vertices in the proposed method. The figure on the right shows a point set, and the figure on the left shows the convex hull. First, all points are projected onto a straight line as shown in the figure. At this time, when the projection points of certain points became the end points, the point became the convex hull vertices. Therefore, the convex hull is computed by continuously rotating the straight line and computing the convex hull vertices each time. However, in the actual computation, the rotation is discrete. Therefore, an approximation is introduced. At this time, if the step size of the rotation is large, an oversight of the convex hull vertices increases. Therefore, an accuracy gets worse. In the figure, there are 3 oversights, and the figure on the right shows the approximated convex hull. On the other hand, if the step size of the rotation is small, an oversight of the convex hull vertices decreases. Therefore, an accuracy gets better. In the figure, there are no oversights, and the approximated convex hull matches the exact convex hull. The behavior of the FPGA implementation of this method is shown in the figure below. Set multiple straight lines inside the FPGA in advance. Then each straight line receives an input point and computes the convex hull vertices by updating the endpoints. Green points are endpoints in positive direction of the straight line, and yellow points are then endpoints in negative direction of the straight line. Then enzympt and the computation of convex vertices are completed. The approximated convex is output by reading out the vertices in a counterclockwise order as shown in the figure. The number of clock cycles is determined by the number of input points. Thus, an approximated convex is computed by the linear times of the number of points. The circuit diagrams actually implemented it as shown in the figure. The rectangular is a circuit called inner minimax, which consists of M. 4 straight lines are set for each, and 8 convex vertices are computed. The circuit receives 1 point every clock cycle. The vertices are output in counterclockwise order from out to N. The evaluation used the 26 types of point sets used in the first related works of GPU implementation. The number M of inner minimax circuits was changed from 50 to 350. Resource usage and accuracy were evaluated, and the execution time was compared with QHAL and CUDA chain. The evaluation environment is as follows. It is the result of resource usage and maximum operating frequency. Each time M was increased by 100. LUT utilization and FF utilization were increased by about 12 points and 8 points respectively. Assuming a linear relationship between resource usage and M, the target FPGA can implement the system up to M equals 750. Also, when M was 150 or more, Fmax was about 180 MHz. And when M was 50, Fmax was close to 300 MHz. Therefore, the smaller M, the higher the maximum operating frequency and the higher the speed. It is a comparison result of execution time. The horizontal axis of the graph is 26 types of point sets and their sizes. And the vertical axis is the speed up ratio to QHAL execution. When M was 50, it was 18 to 30 times faster than QHAL and 5 times faster than CUDA chain. Also, when M was 150 or more, it was 11 to 19 times faster than QHAL and 3 times faster than CUDA chain. Approximation was evaluated with 3 indicators R, eta, mu. The first index R is the ratio of the points that are the vertices of the approximated convex hull among the vertices of the exact convex hull. The second index, eta, is the relative error between the exact convex hull area and the approximated convex hull area. The third index, mu, is the value obtained by normalizing the largest deviation between the exact convex hull and the approximated convex hull by the diameter of the point set. When mu is close to 0, it seems that there is almost no difference between the exact convex hull and the approximated convex hull. First, this figure shows evaluation result of R. As M increases, R increases. Thus, the accuracy improves. This time, only 4 approximated convex hulls achieved R equal 100%. Next, this figure shows evaluation result of eta. As M increases, eta decreases. Thus, the accuracy improves. The maximum value of eta was 0.037%. Thus, it seems that there is almost no differences in area between the exact convex hulls and the exact approximated convex hulls. Last, this figure shows evaluation results of mu. As M increases, mu also decreases. Thus, the accuracy improves. The maximum value of mu was 0.038%. Thus, it seems that the exact convex hulls and the approximated convex hulls are almost the same. Then it is a summary of this work. In this work, we proposed an approximated convex hull algorithm suitable for FPGA and implemented and evaluated. This system has low latency because it executes point input and convex hull computation in parallel and can compute the approximated convex hull without pre-sorting of points. Execution time, resource usage, and accuracy can be adjusted by M. In the evaluation, it was 11 to 30 times faster performance than the library Q hull. The maximum approximation error, mu and eta, were close to 0, respectively. Thus, depending on applications, the approximated convex hull by this method can be used instead of the exact convex hull. Future work includes expansion to 3 dimensions. However, the complexity of the inner minimax circuits limits the number of instances that can be instantiated. In addition, more straight lines are needed than 2 dimensions. Therefore, there may be a problem that the accuracy becomes worse. If this can be implemented in FPGA, high-speed approximation computation of 2D triangulation can be expected. That is for my presentation. Thanks for listening.